So we look at some epidemic scenarios when you are comparing that of a random graph to a scale-free graph. You realize that, as is expected, you can see that if red represents the infected people, by time um, 40 or 30, that's when we have our highest peak in the number of people that are infected. But if you are looking at it for the scale-free graph, you realize that just by time 20, we are already reaching our peak for the number of people that are infected. And in fact, you realize that this is even higher, as about almost 200 as compared to that of the random graph, which is about 150, based on so many simulations that were made. This just tends to prove the fact that an epidemic spread is much highly likely to travel faster in a scale-free network in comparison to a random graph. This shows you a similar scenario for the small world graph, how likely an epidemic is to spread. So we took the various parameters and wanted to analyze how they affect epidemic spread in various networks. When we look at that for relative infectiousness, we tend to realize that the higher the relative infectiousness goes as compared to the epidemic time scale, we have the scale-free network having the shortest time scale for the spread. So you realize that just around 40, as the relative infectiousness increases, this decreases slightly, showing you that within a very short time, the scale-free network is highly likely to have a higher epidemic spread. Red shows the random network, which comes next. Then we have the small world with the small world graphs, which is a more which shows you how the relative infectiousness is actually affected by the time scale in an epidemic graph. This graph shows you the number of people that are affected by the relative infectiousness. If you are looking at these as well, you realize that within even the smallest relative infectiousness, we have a number of people already being affected in the scale-free graph, which then also verifies the point that the scale-free graph is highly likely to have a faster spread of epidemic with the least relative infectiousness in comparison to the other graphs. This graph basically shows you the critical values, I mean the values at which you have the highest number of people already springing up with diseases for a specific relative infectiousness. I realize that the critical value for the relative infectiousness for the random graphs is between 0.15 and 0.2, right around here. You realize that a lot of people at this point are starting to already, it's rather graph represented in red. You can see that a lot of people around here already showing some signs of infectiousness. And when you look at that for the scale-free network, you realize that it's already between 0.5 and 0.1. A lot of people already here start to show level of infectiousness. This just verifies the point again that the spread of epidemics in a scale-free network is much likely to be higher, irrespective with smaller relative infectiousness as compared to the other graphs. Another parameter we considered is the network size. We wanted to see how the network size affects the epidemic spread. So we looked at different network sizes, like 50, 100, all the way to like 1,200, and compared it to the epidemic time scales. You realize in here that based on the network size, the number of infected people per time scale varies in comparison. If you are comparing, for instance, the random graph to the scale-free graph, you realize that the scale-free graph tends to, have a steady growth around it in the network size, though in random size, since it's very randomized, anybody could get it. So you realize that if you are looking at the 1,000 points, for instance, there are about 60 people or 50 to 60 people that already, we already have so many people infected at this point, at this 50 to 60 time points, in comparison to that of the scale-free network, where it's about 40 to 50. Because you realize that, as I said in the definition, just one person might have the highest link, and it's more or less going to gather a lot of people. So if the larger the community is, it's very likely that a lot of people will be infected within a short period of time. This shows you a typical graph about which is with respect to the the epidemic time scales with the number of people in the epidemic. So you realize that if you're having about 10,000 people and it's with respective time scales, you see that the scale free network, the larger the network sizes, with the epidemic size, so the number of people that are infected tend to be less when the graph is growing bigger. It's just like considering the Hong Kong issue with SARS. Realize that though one person affected a lot of people in Hong Kong, because the number of people on Earth is actually very huge, it tends to be smaller since it's mainly Hong Kong that is being affected, and that one person is like has the highest link. But if it's more of relationship based, and it's more of the correlation between people, we realize that there's a likelihood of higher spread because people will be traveling around and the disease will be spreading much higher, as shown in the small world weighted network as the graph size increases. Another parameter that we also considered is the infectiousness vector. This basically shows you, we chose different vectors. So one with the standard vector that was used in all the other examples, and one with the long latency time and no latency time, just to see how the infectiousness vector affects the epidemic spread. You can see from these graphs that in fact the infectiousness vector tends to be very steep and falls immediately, as shown in the random vector. If you compare that to the small world weighted edges, right, that's shown right here. This again just verifies the point of epidemic spread across all the various networks as discussed. The final parameter we took into consideration was the mean degree. You can see from here that if we have a lesser mean degree, maybe a mean degree of 4, like D being 4, it means that there's less connectedness of the graph, and you see from that right here that leads to less number of people being infected. If there's a high connectedness in the graph, a lot of people are connected with each other and know each other, realize that the number of people that are affected within a short time period increases really much, as shown here. And realize that this is very similar for all the other graphs. At this point, I'll take you through my MATLAB programs. I wrote MATLAB programs to more or less show you to make up a graph for all the 4 graph types and show you an example of an epidemic spread and how it starts and how it goes. So as you can see, this is my final project graph. It shows you just the number of infected people and the number of resistant people, which how the epidemic is. It shows you that if you count it 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9 steps, the epidemic does come to an end, and everybody becomes resistant for this particular graph. If you run it again, realize that it shows you a different value again. This just shows that there are different simulations and different parameters that will be based, since this is very randomized. These other 4 algorithms just show you the kind of graph that's for the different graphs. So I did that, the small world, the scale free, the random, and the small world with weighted averages. So if you play this graph, you realize that it gives you an example of the small world with weighted averages. So if you play this graph, you realize that it gives you an example of the small world with weighted edges. Based on this, I like to I also discussed some other related work, which is the successful infected removed models and the freeze models. I've shown this in my project's final report, and that is open for reading, and you can find that and read more on it. I'd like to thank you for listening to my presentation.